Hi, I'm Alistair, and in this video I'm going to explain how to use an old rotary dial telephone like this one and an Arduino to do interesting things. And those interesting things might be playing a sound file saved on an SD card down the telephone headset, or they might be that when you dial a particular number on the telephone you might unlock a maglock like this one. Now, there are a couple of videos already I've seen on YouTube of people using rotary dial telephones, but most of the ones I've seen involve sort of taking the rotary unit out and kind of soldering or wiring direct to the pins on the rotary interface. And I think that's a terrible shame, because I think these are lovely aesthetic items. This is a GPO 746 telephone, and in the UK at least, in the 1970s and 1980s, pretty much every household had one of these phones. So I grew up with them in the house, and I think there's something sort of incredibly satisfying. They're quite weighty, they've got a good solidness and durability to them. So I think it's a great shame to take them apart to use for a puzzle. So all I've done in this example here is I've spliced into the cable, and there's 4 wires in one of these telephones. There's a green, white, blue and red. I'd love to tell you what the correct names for those wires are. I'm not a telephone engineer. And this comes back from the days when it's not as simple as sort of saying one of those wires is for the speaker, one's for the microphone, one's for the dial tone, one's for the ringer. They didn't work like that. In fact, each of these cables would have had multiple functions. So when you lift the handset, there's a voltage change on the line that could be detected at the exchange. The sound waves themselves are sort of modulated with other signals on the wires. So I can't explain exactly what this calls, but I will simply call them red, blue, white and green. I've wired those into my Arduino. Then I can use those as outputs to receive the dialing code, and I can also use them as inputs to send signals to the earpiece here. So for example, let me show you what I can do. So if I dial a particular number, so in the UK at the time when these were popular, everyone had 5-digit phone numbers, for example, and I can still remember my old phone number now. Oh, actually, before I do that, hang on. Let me put the serial monitor on so you can see what the Arduino is seeing. Here we go. So here's the output for my serial monitor. So when I lift the handset, you'll see it says receiver lifted there. I'm now going to dial my old phone number from early 1980s, let's say. That's 2 1 8 0. Listen to that dial, wasn't that wonderful? 7. And you see each of the digits have been dialed on there on the serial monitor. When I release this last one, it will detect I've done a valid string of 5 digits, and what you should hear is a sound file being played through the speaker here. So sure enough, if I hold that up next to the mic, hopefully you can hear this. So this is a public domain recording of a Radio Australia broadcast, I believe, but I hope you can hear that. That's enough of that. Let me put that back on the hook. So that's one example of what you can do. For another example though, let me dial a different phone number this time. So this one's a bit easier to remember. This is just 1 2 3 4. You can probably guess what the last digit would be, and when I do this, watch the maglock at the top here. Hey! Okay, so let me talk you through the wiring of this, and as before, it's probably easier if I show you the diagram in fritzing rather than the real thing. Now I've built it on a breadboard here just to show the ease of connections, what's going where. But obviously if you want to build this for a real puzzle, you'd probably want to put that onto a PCB or a protoboard or something like that. But I think that might be the video I might do in the future will be about moving to production kind of rather than doing stuff on a breadboard. But for now it's on a breadboard. So here's the main processor. I'm using an Arduino Nano, but you could use any Arduino or similar device really. And I've got this SD card reader up here, which is plugged into the SPI interface. Now, I've sort of described that in some videos in the past, but there are certain pins on the Arduino which are assigned to use for different SPI functions. So there's a thing called the MISO line, that's the master in slave out line, and that always goes to pin 12. You've got the MOSI line, this blue one, that goes to pin 11. The system clock line, this yellow one here, that goes around the back and into pin 13 on the Arduino. On a Nano, pin 13 is on this side of the board. If you're on an Uno, pin 13 is kind of in a line next to the other one, so that's why this looks a bit messy here, because it's going around the back to the next pin. And then you also need to assign a select pin. I'm using pin 4. You can assign that to a different pin if you want to, but 4 was just available while using it. Now, a little note about the power here. SD cards themselves are always powered by 3.3 volts, but sometimes the reader unit, like the one I've powered here, actually has a 5 volt input, and then it has a regulator on board the module itself to reduce that voltage down to 3.3 for the card. So be a little bit careful, depending on exactly which unit you've got. It might want a 3.3 volt supply direct, or it might want a 5 volt supply which it regulates down, or maybe you've got the option of both. So I'm using 5 volt here because that's what my particular card had, but you may want 3.3 instead. So the SD card itself is what's being used to hold the audio clips that are going to be played down the earpiece. A Arduino itself has a very small amount of onboard memory, just about enough to hold the program code that you're actually running itself and maybe a tiny bit of data. But if you want to hold kind of audio files like WAV files or MP3 files, something like that, you really need to store them on some external storage. So that's what we're going to use the SD card for. Okay, and then coming down here is actually where I have the telephone itself. Like I said, there are 4 wires coming out of a BT standard telephone: red, green, white and blue. And I've got the red wire going to pin 9. That is going to be used to carry the audio output into the earpiece. I've got the green wire going to pin 8. That's going to be used to detect whether the phone has been lifted off the hook or not. And the white wire is going to the Arduino ground. So I've got the white wire going to the rail here, and then that pin there is connecting it to ground on the board just up there. Okay, so those 2 components are what's used for when you dial a number and then hear a audio file be played in the earpiece. Now, the other components on the board are used for the other function of the puzzles. This is when you dial a number and the maglock gets released. So first of all, I've got a relay unit here. So a maglock requires 12 volts to run, but the Arduino can only output a 5 volt signal. So it's like a logic level signal coming out of here. So the relay is used to switch a 12 volt circuit on this side from a 5 volt logic level signal on this side. That's what the relay is for. But actually it's a little bit more complicated than that even, because I'm using a relay that has what's called an opto-isolator. Now, I have talked about these a little bit before. Normally you can get the transistor coils of the relay to be powered by the same device that's actually powering the input signal. So normally what you do is you plug the Arduino into this side with ground and a 5 volt supply and a signal line, and what that does is when the signal goes high, it activates the relay, closes the switch and allows power to flow on this side. Now, this particular circuit, however, is very sensitive to electrical interference and feedback, because we're actually sending an audio signal down the line from the Arduino here. What we really want to do is isolate the Arduino completely from anything that might cause kind of a power disturbance, and that involves when you activate relay coils and turn them on and off. You can get kind of a spike on the line going back into the Arduino. So to avoid this, we're going to use this feature called an opto-isolator. So what happens here is that the relay coils themselves are actually being powered by a separate, completely isolated 5-volt supply that's coming in from this DC jack here, and that's going to the pin labelled ground and to another pin here called JD VCC. So that's the voltage supply that is going to power the relay coils. Now you might find that there's a jumper that connects JD VCC to VCC. If that's the case, what you want to do is remove that jumper because what we want to do is to isolate the power supply just so it supplies the coils. And then on this side, what we're going to do is we're going to connect the VCC line to the Arduino 5 volts. And we're also going to connect one of the input pins. So I'm using the second relay here. So I'm actually going to in2. If this was a single relay block, there'd just be a single in pin. I don't actually need it to be a dual relay for this puzzle, but I've got I happen to have this component available, and it had an opto isolator, so I'm using that for this purpose. And obviously, you could have another load driven from this relay, which gets activated when you dial a different phone number instead. So when you've got it set up like this, the only thing that the Arduino powers here is actually a little, it's like an LED basically inside the relay. So this 5-volt signal here and this input, all this does is drives a LED on or off. That is then detected by an optical detector, which uses the 5-volt signal that's coming through this line here from the DC to power the relay, to close the relay switch. And then when that's closed, it allows 12 volts on this side to release the maglock. Okay, so it is a little bit more complicated than some of the other circuits I've shown in the past. But the reason for doing that is it means that the Arduino is completely isolated from this power load here. All it's doing is powering an LED. So it's kind of got an optical isolation barrier. And that is why it's called an opto isolator. So the wiring here, just to say again, so if there is a jumper that connects JD VCC and VCC, you take that off and you plug JD VCC into a separate DC power supply and the ground into that as well. And then you take this VCC line here to 5 volts on the Arduino, which is coming up this rail here, and you take this to the pin that is going to drive the relay to close it. And then finally, when that closes, what it's going to do is it's going to flick the connector here over from the normally closed side into the normally open side instead. That's going to connect these 2 red wires here, and it's going to allow current to flow from the 12-volt barrel here into the maglock, and that's going to spit out the lock there. Okay, so now let me talk you through the code that's running on the Arduino here. It's reasonably complex code. It's got several sections to it, so I'll step through it a line at a time. But what I'll do is I'll concentrate on the bits that are specific to this puzzle. So if there's bits that I kind of go over a bit quickly, it's probably because I've covered them in one of my other videos somewhere. Okay, so start at the beginning. As always, I define a different mode if you want to output extra information to a USB serial connection. So I've just got to define here for debug. And then I include some of the libraries I'm using. So the SPI library, that's for any device that's connected via the serial peripheral interface. And in this case, what we're using is the SD card reader. So we also include the library that's specific to that we use the SD card. Now, in terms of the audio output that's being played over the telephone earpiece, I'm using this library here called the TMR PCM library, which you can download from GitHub at this link here. Now, there's quite a few configuration options and things you can change in that. It's pretty well documented on the GitHub site itself. But the main change that I made was in this file, the PCM config header file, which I just load up. Quite near the top of that, There's some various settings and things, and this setting here, define buffer size 254. So I think originally that was commented out like that. I uncommented it and put this 254 value here. What that's going to do is will increase the amount of memory that is allocated to use as an audio buffer, and that will increase the playback quality. That's all that's for. Okay, so that is the library. Other than that, there. I mean, you can use it without making that change. I just did that because I found that improved the quality slightly. Okay, and then we declare some constants that are used in this sketch, and we declare the pins that are going to be used. So again, if you consult back to the wiring diagram, I'm using pin 9 for the red wire from the telephone, pin 8 for the green wire, pin 2, that is my output that's going to the relay, which is going to activate the maglock. Pin 4 was my chip select pin, which is going to the SD card. And also, just in the comments up here, I just mentioned the white wire from the telephone also goes to the Arduino ground. And then here we've got some constants that are settings to do with handling of the dialing on the rotary dial. So whenever you have any kind of... The way the dial works is as it spins round, there's two metal contacts that kind of open and close a connection, which sends a brief pulse, which can be read by the Arduino. And it's counting up those pulses will enable us to determine which digit was dialed. But with any kind of reading of a contact that opens and closes like that, there's a risk of what's called bouncing, which is where kind of if you read it too frequently, you can get a bit of chatter. You get on, off, on, off, on, off, and then it finally settles on the correct state every time it changes. So the debounce delay here, this is just a small value, it's 5 milliseconds, and what that says is after a state change has been detected, just ignore any state changes in the following 5 milliseconds just to let that reading settle down again before we try to take another reading. So that just increases the quality of the dialing number that you'll get received. So like I said, the way that numbers are dialed is it's when you release the dial and it spins back to the position again, as the dial moves around, it opens and closes a connection with a series of pulses. But then obviously when you dial the next number in the telephone number, the next digit rather, you'll get another series of pulses as well. So we need some way to tell the difference between which are the pulses that are all related to the digit being dialed at the moment, and then when does the first pulse of the next digit being dialed begin. So that's what this value here determines. So we're saying that 250 milliseconds, quarter of a second, that's the longest delay within which two pulses will be received and for them to be considered part of the same digit still. So if we have 3 pulses that are like pulse, 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 that will be the digit 3 being dialed. But if you have pulse, pulse, and then a gap, and then pulse, that will be the number 2 being dialed, followed by the number 1 being dialed. Okay? So that there. You might need to change that depending on if you're on a different telephony system or a different kind of style of rotary dial. That seems to work pretty reliably for me. And then this will be the number of digits that need to be dialed before the program will look at what number is dialed and determine what to act on it. So like I said, in the 1980s or 70s when this telephone was from, in the UK, we had 5-digit telephone numbers. But you can change that to anything you want. If you want it to be a 4-digit code because that goes with some sort of padlock in your room or something like that, you can just change that number to a different number of total digits in the phone number. Okay, so there are the things which are not going to change throughout the duration of the puzzle. Those are our constants. And then we'll go on to look at the globals. So the global variables are things that are going to be accessed throughout the code. So we create an object. This is the TMR PCM object, and that's going to handle all of our audio output. We'll create a variable for the number that has been dialed. Now, I'm creating this as a character array. You might think that a phone number would be best stored as an int or some other number. But actually that doesn't work very well because phone numbers could begin with the digit 0, for example. So 0, 1 as an integer would just be 1. You'd kind of lose the leading 0. So I'm storing it as a character array instead, as a char array. And it's going to have the number of digits in the phone number in it, and then one more at the end, because character arrays have to be terminated with this character at the end. So we're leaving one more item in the character array just to store the string terminator at the end of it. When we're dialing a 5-digit number, let's say, we're going to keep track of which of the digit we're dialing at the moment. So this is a counter, just to count up which digit we're currently dialing. And this is another counter that's going to count how many pulses have been counted in the current digit that's being dialed. So, like I say, the number 5 would have 5 pulses in a row. The number 9 would have 9 pulses in a row. The number 0, or the digit 0 rather, is an interesting one because that has 10 pulses. Obviously, 0 pulses wouldn't be able to be detected that there are any pulses at all. So the number, or the digit 0, has 10 pulses to it. All the other digits have the number of pulses equal to their value. And then we define a couple of states that the puzzle can be in. It can be on the hook, so that means that the handset has been replaced on the, or the receiver has been replaced on the handset, the phone's not doing anything. Off the hook, so someone has lifted the handset up. Dialing, so they're in the middle of dialing a number at the moment. And connected, this is when they've actually finished dialing a number and they have been connected to it. This is just a little helper variable to remember whether the last pulse heard on the line was a high or a low value, just to tell whether that's changed. And this was the time that the value was last changed, which we'll use to compare whether we're still in the same digit or in the next digit along next. And this is a value just to record the current time. So millis is an inbuilt Arduino function that will tell you the number of milliseconds that have elapsed since the program has been running. Okay, so then we go into setup. So the setup function will get called once when the program first starts and every time it resets. So most of this is pretty basic initialization. So we're going to initialize both the phone pin and the hook pin as input pull-ups to start with. Now remember what I said about actually when these phones were designed, those signal lines had multiple functions. They were used both to carry audio signals to the earpiece and also to carry the microphone signal of the spoken word of the person talking, and to ring the bell and to dial the digits and all the rest of it. So I've called them phone pin and hook pin in the code because that's the purpose for which we're going to be reading them. And to start with, they're going to be inputs, because the first thing we're going to want to listen for is whether the handset has been lifted up and the person has started to dial a number. So to start with, there'll be inputs, so that we'll actually change their function as outputs later when we want to send an audio signal down that same line instead. The electromagnetic lock is connected via a relay onto this pin here, and it's an active low relay, so we initially start it with high output, and then when we unlock it we'll drive that low instead. We'll start a serial connection, which we'll just use to output some debugging information. And then what we do here is we initialize the SD card. So the chip select pin, which we were using pin 4 as, we start a connection to the SD card reader using that pin. And if that is not successful, we print out a message saying that the SD card has failed, and we just jump out of the function here, so we return. If that is successful, we'll carry on. The next two functions are a little bit about just audio configuration. So I'm going to set the volume of the output. This is a value between 0 and 7. If you turn it up too high, then you'll get distortion on the line. If you turn it too low, obviously you won't hear it at all. So 4 was a value that worked well for me, somewhere in the middle. And you can also just set this value here to increase the quality of the audio output slightly. It enables oversampling. If you want to turn that off, you can just change that value to 0. And that's the end of the setup function, so we'll just put a little serial pin here. Okay, so then we go into the main program loop. So this is where kind of all the work is done to actually listen for dialing and send the audio message and unlock the lock and everything else as well. Okay, so the first thing we always check on every iteration through the program loop is the receiver lifted off the handset. So to do that, we're going to read that hook pin, so whether the phone is on the hook or not. So we're going to see it. And then we're going to compare it to the previous state that the telephone was in. So if the last time we stepped through the loop function, the phone was on the hook, so that means that the handset, the receiver was placed on the handset, but now it's been lifted. What that means is that in this frame, the person has actually lifted up the receiver from the handset. Okay, so we'll put some input to say the receiver's been lifted, and we will progress the state of the puzzle to say, okay, the phone is now off the hook, so it's ready to be dialed. This section here, this is kind of like the opposite of that. So this is saying, okay, well, if the last time we stepped through the loop function, the phone wasn't on the hook, but now it is, that means that the receiver must have been replaced in this frame. So we'll put some information onto the serial connection just to say that as well. We'll reset the puzzle state back to on hook again. So remember, this is kind of the default state of it. And if we were in the middle of counting any pulses or digits, so if we were kind of halfway through dialing when the phone was put back on the hook, we'll reset those. We'll stop any audio that might have been played through the earpiece, and we'll also reset the phone pin back to its default state so it's ready to listen for if the phone handset is picked up again. Okay, so the next possible combination. So what if the phone is currently off the hook, or we were in the middle of dialing a number? So this means that the person's got the handset in their hand, and either they've just lifted it off this frame, or they previously lifted it off when they started dialing. Okay, well, what do we do in that case? Well, the first thing we want to do is work out what the current time is, and then we're now going to listen to the phone pin. So up to now, we've been listening to the hook pin, which is the one that tells us whether the handset's been lifted. We're now going to listen to the phone pin, and that's the one that changes when the dial is turned. Okay. So we're going to see whether the reading of the phone pin is different from it was in the last frame. And if it's changed, that means that the user must be in the middle of dialing a number, because we know that that phone pin has switched state since last time, so the dial is rotating somehow. Now this is where that bit about debouncing I was talking about before. So if it has changed, but it's been less than the debounce delay since the last time it changed, so if it's been less than 5 milliseconds since the last time it's changed, we're just going to ignore that change, because what that probably means is it's just a little bit of electrical bouncing on the signal, and we're not confident that that's definitely a change in state, so we'll ignore that. If, however, it's been longer than that debounce delay, we'll carry on going. So we'll assume that this is actually a true change in state from the last time we measured it. And in that case, what we'll do is we'll increase the pulse count. So the user's dialing a number, the dial has twisted round, and it's been longer since the last state of change, so we're confident it's changed. We'll increase the pulse count. And we'll also update the time at which the pin was last changed, so that next time when we step through this loop, we'll know to use the current time to compare to. And we'll also update what the previous reading was. Okay. So that's how the pulse count is increased. Now we're going to the next bit, and we'll say, okay, if the time since the last time the pin was changed is greater than the longest amount of time we'll wait to listen for pulses within a single digit, and if we've received at least one pulse so far. So we've definitely had at least one number being dialed. As more and more pulses are received in that same digit, we're adding them up here and here over and over. So we've got a total count of the number of pulses we've had this digit. But now we've also waited long enough to make sure we've definitely captured all the pulses that could be part of the digit currently being dialed. What we'll then do is we'll see whether the length of all the digit dials has been equal to the number of digits in a phone number. If we haven't yet dialed a complete phone number, so we've dialed something less than 5 digits so far, what we'll do is we'll put some output on the screen. Remember I said that actually the digit 0 is 10 pulses long, because it can't be 0 pulses because we wouldn't be able to measure it. So that's what that line here does. It says, okay, if we've actually detected 10 pulses, what we've got is the digit 0. We'll display some output as to which digit's been dialed. We'll add the pulse count onto the end of the current number that we're storing that's been dialed. And we'll move on to the next digit as well. And what we'll just say is we insert kind of a placeholder digit into the end of the line, so that when we come onto it next time, what we can do is we can add the true value on. That's what this line does. So this is like a placeholder. We'll put in a 0 there, and then what we'll do here is we'll add the true number of pulses onto that placeholder to insert there. So that's if we haven't dialed a complete number yet. That's what that is. If we have dialed a complete number, then we fall into this section here. So if we've added up the current digit, that's the number of digits we've dialed so far. And if the number of digits dialed so far is equal to the total length of a phone number, so 5 digits, let's say, what we'll do is we'll put onto the screen the complete number that's been dialed. And then what we're going to do is we're going to put some if statements to compare that number to some of the numbers that are actually going to perform a function. So this str_comp here, this compares two strings. So what we're going to do is we're going to compare the number that's been dialed to this string here, 21807, and we're going to say if the comparison between them is equal to 0, that means that there's no differences between them, so they're exactly equal. So that's a sort of a roundabout way of saying is the number that's been dialed 21807. Okay, and you can replace this with any 5-digit number you want here as well. If that's the case, what we're going to do is we're going to play the sound effect. So we'll write serial.println, just so we've got something on the output. Now, this is the phone pin, which earlier on we were listening to detect what digits have been dialed. Now what we're going to do is we're going to use that same pin as an output, and we're going to output the audio to the speaker, to the earpiece through that same pin. So we're going to set the phone pin as an output, and we're also going to assign that as the speaker pin that's being used by the TMR PCM library. You'll see a note that this is a note from the library itself. So on Arduino Uno or Nano, you must use pin 9 here for your phone pin. If you're on a Mega, you've got a wider choice of pins. You can use 5, 6, 11 or 46. Okay. And then this play command here, this tells the library to play a WAV file, which I've just saved. It's just called music. It's got no extension on the end of it, so it doesn't have .wav or anything. It's just music, and that's saved on the SD card as music. And that's going to play that onto pin 9, which we've set as an output, and that is going to play through the earpiece. And then what we're going to do is we're going to loop round and round. So this music is going to carry on playing until the hook pin has been replaced. So basically, while the hook pin reads as a low signal, that means that the phone is still off the hook, and we're listening to the earpiece. We're just going to carry on letting this play, and this will play. This is an asynchronous function, so this will carry on playing even while the code is delaying here. That will just carry on going round and round. And obviously, as soon as the phone is replaced on the hook, the code will then carry on and jump onto the next line. Okay. So what about if we dialed a different number instead? Well, let's suppose that the number dialed was 12345 instead. So again, we'll use this str_comp comparison function. If that's the number that's been dialed, this is where we're going to release the maglock instead. So we'll send a low signal to the lock pin. Remember that the way that the relay is set up here is that a low signal releases the maglock and a high signal locks it again. So we'll send a low signal, we'll just wait for 100 milliseconds, and then we'll send a high signal again just to deactivate that. So this is a momentary maglock, so we only need like 100 milliseconds. That will be enough to spit that catch out and then lock it again. If you have one of the other sorts, if you have like a fail-safe maglock, you might need to adjust the timing there so that the lock opens for long enough to open whatever door or hatch or whatever it is you want it to do. But this is the amount of time that the lock will be energized for, essentially, before carrying on. Or if we get into this else function here, so what this means is we've got this far, we've compared it to this number first of all, and if that was true we did this, then we compared it to this number, we did this. If we got to this bit, we have dialed a complete phone number, we've dialed 5 digits, but it didn't match any of the particular phone numbers we were listening out for. So let's do something else instead. And what I'm doing here, I'm actually playing a different sound effect. So I'm playing a sound effect called bomb.wav, which is kind of exploding sound effect. I'm not quite sure why the phone would explode if you dialed the wrong number, but for whatever reason, that's what it does in this example. So we play that, and then we introduce a bit of a delay. And finally, we set the state of the puzzle to connected, just to show that the state of the puzzle has changed. And then right at the end, we've got all the way through. There's just this line here that says pulse count equals 0. So we've got through the whole loop, we've waited, we've listened if we've had the total count of pulses, and we've processed them that have been received. So let's reset that before listening again to the next digit that could be dialed. And that's the whole code. So there you have it, that's the complete puzzle. You could probably do other things as well. You could interface to the microphone on one of the other pins and listen for a particular sound that was said or something like that. I think, like I say, these are wonderful items. This is working with a GPO 746 telephone, which was, like I say, in the UK from the early 1980s, and I believe that this setup will work with any equivalent telephone from around that time. I don't honestly know what the telephony systems are like in other parts of the world. I believe they will be similar to this, but they might have a slightly different setup. So if you do get this to work in another country, please let me know in the comments, and I'll include that in for other people to be able to see. If you want to download the code listing, which is running on the Arduino, or if you want to access the wiring diagrams, a link to that will be in the comments as well. So I hope you found that useful, and thank you very much for watching.